Okay, this is 3.3 Features of Functions, and this is a practice understanding task. And this is one of my favorite activities in Module 3 because it really puts together all the notations that we need to understand for features of functions and communicating those features. And it also, we have to go back and we have to use some of the things from Module 1 and Module 2 so we can come up with different models so we can really determine the features of said functions. It's a little tedious, and I have no doubt when this is finished, this is going to be a long video, but I'm going to do my very best to make this a very informative video that can become a tool for all of our integrated Math 1 students. So here we go. For each graph, determine if the relationship represents a function, and if so, state the key features of the function, intervals where the function is increasing or decreasing, the maximum or minimum value of the function, domain and range, x and y intercepts, etc. So we have a graph over here on the right, and then we have our key features of functions format right here, where we'll just fill this out, which will cover every possible feature or function we could ever talk about. So number one, is this graph the graph of a function? Yes or no? All right, and so when we have a graph, we like to check to see whether or not it's a function by using the vertical line test. So you picture a vertical line, and is there anywhere on this graph where we could draw a vertical line that would cross it at more than one point? There's not. So that means every input has one and only one output, and therefore this is a function. So we'll circle yes. Now the domain. So early on in this activity, I'm going to go ahead and project the graph onto the x-axis so you can actually see a graph of the domain. And then we'll do the same thing with the range too. But if I project this piecewise linear function onto the x-axis, just picture it coming down onto the x-axis. It would go from x equals -3 to x equals +4. Guess what? That's the domain. And let's work now on our interval notation to show that. And because x can equal -3 and x can equal 4, we use solid dots on our endpoints, and that means in interval notation we're going to use brackets. So I have a bracket on the left, a bracket on the right, and my left endpoint is that -3, and my right endpoint is the +4. Now for the range, we're going to project the graph onto the y-axis. So you see that my minimum y value is 0, and I see that right there, and my maximum y value is 4. So the range, and again, note the solid dots because y can equal 0 and y can equal 4. So I'm going to go bracket, bracket, and my interval notation, I'm going from y equals 0 down here at the bottom to y equals 4 for this maximum point right up here, point B. And there you go. Now interval notation is, we're talking about the closed interval from -3 to 4, and that means everything in between and including -3 and 4. Same thing with the y's for the range. It's the closed interval from 0 to 4, and this means everything between 0 and 4, including 0 and 4, including the endpoints. Now, the extrema. Well, we're looking for the lowest point on the graph and the highest point on the graph. And we want to write those in as an ordered pair. So there's my lowest point, x equals 4, y equals 0. So let's just go 4, 0. And that would be my minimum. And focus on your y value. The minimum y value on that graph is a 0. Now what's my maximum y value? Well, be at that point right up there. And write that as an ordered pair. So x is 1, and the y coordinate of that max is 4. So here's my minimum value as an ordered pair and my maximum value as an ordered pair. Now, increasing or decreasing. Well, this graph is increasing from -3 to +1. Let's go ahead, maybe we'll project that onto the x-axis too. Let's see if I did that. Yes, I did. So again, it is increasing in the closed interval. That's why we have solid dots, from -3 to +1, and that's talking about this part of the graph right here. Okay, so let's represent that in interval notation with a bracket because of the solid dots, and then the left endpoint is the -3 and the right endpoint is the +1. Now, on what interval is this graph decreasing? Well, it would be from point B to point C right here. So let's go and project that part of the graph onto the x-axis. And note that is the closed interval, solid dot, solid dot. So I'm going to go bracket from x equals 1 to x equals 4. You guys can probably hear my dog barking in the background. I'm sorry, she's very excited. Maybe one of my family members has come home or something. Okay, don't let that distract your learning, please. Now, intercepts, if they exist as ordered pairs. Okay, so intercepts, that's simple enough. Does this graph touch the x-axis or the y-axis? Well, that looks like an x-intercept right there, and we could write that as an ordered pair. And the x-coordinate would be 4. And at the x-intercept, the y-coordinate is always 0. Now the y-intercept. Okay, right there. Now, sometimes we have to approximate, you know, and again, you and I might not approximate this point exactly the same. That's okay. It's how we see it. So let's write this as an ordered pair. Now, I think we can all agree that the x has to be 0 for the y-intercept. Note, at the x-intercept, y is 0. At the y-intercept, x is 0. Now, what are you and I going to call the y-coordinate of that point? Well, I see it's a little bit above the 3, so I probably call that like a 3.2 or something. Let's find out. Yeah, 3.2. Now, if you had called that 3.1 or even 3, that's your approximation, and that's okay. All right? Now, function notation, f of 1 equals what y value? Remember, this is my x. So when x is 1, what is my y coordinate? So we're talking about that point right there. And what's the y coordinate of that point? That would be the 4. Okay? Now they say f of what x value gives us a y value of 2.5. So let's find where y is 2.5 on the graph. Well, 2.5 about right there. So there's a point right there. Now, again, approximate that x value right there. It's a little bit beyond the 2. So I don't know, 2.1 or 2.2. I did a 2.2. Okay? But now look at this too. Isn't there another point where the y-coordinate is 2.5? And they didn't give me a place to answer that. But let's make sure we do this completely. So do you guys see this point right here? The y-coordinate of that point is also 2.5. So I'm going to write the coordinates of this point in function notation. That's right, we're going above and beyond here. And what's the x-coordinate there? It looks like a -1. And f of -1 equals, again, 2.5. Now, where is this graph positive? Well, it's positive when the graph is above the x-axis. So I'm projecting right here, but notice I'm going to have a solid dot on the left, but over here on the right, the graph equals 0. It is not greater than 0, so it's not positive. So I am going to put an open dot right there at point C. Now this is a graph of the interval where this function is positive. And let's just write that in interval notation. Notice a solid dot on the left, an open dot on the right. This is a half open interval. And I do this like this. I'm going to go a bracket for the solid dot, and that endpoint is -3. And then I'm going to go a parenthesis for the open dot. That's where it's open. And that endpoint is positive 4. Now, this is the half open interval from -3 to 4, where x can equal -3, but cannot equal positive 4. Now, where's it negative? Well, does that graph ever dip below the x-axis? It does not. So it is never negative. So I'm going to say this graph is negative. Empty set. Never. And then finally, for what values of x is f of x greater than 3? So to help me see that, I'm going to draw the line y equals 3. And I call this y equals 3 because you guys know y is f of x. Okay? Now I'm picturing the part of the graph that is above y, or f of x equals 3. And that would be, I'm projecting that down here onto the x-axis. All right? And at this left endpoint, that's where the graph equals 3. So I'm going to have to go an open dot there. And the same thing over here. Let's put an open dot here. So this is the graph of an open interval right here. So instead of brackets, I'm going to use parentheses on both sides. And now let's just approximate our x values. I don't know what we're going to call that. Let's see, that's between 0 and -1. All right, and it's what, about a third or a quarter way there. So you could do something like, I don't know, -0.3 repeating, or -0.25. It's your approximation. So I just did a -0.3. That looks like a pretty good approximation to me. And then how about over here? This point right there. Well, that's an x equals, and that's between 1 and 2. I don't know. We could probably call that like somewhere around 1.75. Let's see what I did. 1.8. How about that? So for what values of x is f of x greater than 3? This graph is greater than 3 in the open interval from -0.3 to 1.8. And these are both approximations. Those endpoints are approximations. And you and I might not approximate exactly the same way. We're just doing our best. Okay, number 2. Oh, look at number 1. There's a lot going on right there, okay? Number 2, I'm kind of excited because if you read the directions carefully, it says, for each graph, determine if the relationship represents a function. And if so, state the key features of the function. Well, guess what? Do you remember the vertical line test? This graph does not pass the vertical line test. Therefore, this is not the graph of a function. We call this a relation. All right? And the reason is the definition of function is every input has one and only one output. And if you look at where I drew this vertical line at x equals 9, it looks like there's an output of -3 and +3. So this graph is not a function because every input does not have one and only one output. Or you could just say, does not pass the vertical line test. All right, let's move on to number 3 then. All right, now this graph looks like it does pass the vertical line test. Yeah, no matter where I draw this vertical line along the plane, it's only going to touch that graph at one point. So that means every input has one and only one output, so it is a function. And what's the domain? Now, well, my left endpoint would be that -6, -8, and my right endpoint would go all the way over here to x equals 10. Looks like I projected again onto the x-axis, and also note my endpoints are solid dots, so I'm going to go bracket, bracket, and my left endpoint is a -8, and my right endpoint is a +10. Okay, now what's the range? Well, those are the y values on this graph. So let's project the graph onto the y-axis. It looks like it has a minimum of -3 and a max of +5. And again, solid dot, solid dot. So we're going to go bracket, bracket. And The lowest y value is the -3, and the highest y value is a +5 right there. All right, these are both closed intervals, domain and range. Now extrema. Well, I can almost see the y coordinates of my extrema based upon the range here. The minimum y value is -3 and the maximum y value is 5. But I need to write this extrema then as ordered pairs. So this point right here, that's the lowest point on this graph. That's the minimum value. As an ordered pair, the x coordinate is -8 and the y coordinate is -3. And my maximum, the highest point, is this point over here far right. And let's write that as an ordered pair. So the x coordinate of that point would be a 10. And the y coordinate of that point would be this 5. And there you go. My minimum value as an ordered pair, my maximum value as an ordered pair. And note how I focus on those y's. Now, increasing. Well, this graph has a peak and a valley. So it looks like there are two intervals where this graph is increasing. So I have to represent both of those. So let's see. Do you agree that at x equals negative, what was that again? Negative 8. This graph increases until it gets all the way to that x value of 0. So I'm going to do the closed interval from -8 to 0. So I'm going to go bracket. Okay, oh, and here's the other one too. From, I don't know, about 5.5 to 10. So let's do both of those intervals with interval notation. Okay, and let me close my iPad. It's distracting me. People are trying to get a hold of me right now. All right, so the first interval where we were increasing was from -8 all the way to 0, and that's this part of the graph right here. And then it begins to increase again from here, which, I don't know, what do you guys want to call that? About a 5.5 or so? I did 5.7. I don't know, 5.5, 5.6. Remember, that's my approximation. All the way to, what's the x coordinate of this point right here? It's a 10. Okay. Now then, when is it decreasing? Well, here's the interval where the graph is decreasing right there. Let's project that onto the x-axis. And there it is right here. So it looks like it's decreasing in the closed interval from 0 to, and again, what did we call that earlier? Let's be consistent here, 5.7. Whew, okay, now the intercepts. Well, does this graph ever touch the x-axis and or the y-axis? Well, that looks like my x-intercept right there. So as an ordered pair, and I'm going to have to approximate this one again, I don't know, is that about a -6.1? Okay, that's what I said earlier. Okay, and the and -6.1 is my x coordinate, but what's my y coordinate at any x-intercept? That's a 0. Simply the coordinates of that point. And now the y-intercept. Well, that's going to be this point right here. All right, so let's write that as an ordered pair. And at the y-intercept, your x has to be 0. But what's the y coordinate? We're going to approximate that. And I probably call that about 4.2. Yeah, there's my intercepts right there. Now, function notation. F of 1 equals what y value? So I go to x equals 1. And we go up, and that looks like about at the 4 right there. Maybe slightly above, but I probably just put 4. I did. And then f of what x value gives us a y value of 3. Well, let's find where y equals 3 right there. So that point right there. All right, so the y is 3, and what's this x coordinate right there? That's also a 3. So I'm going to say f of 3 equals 3. Now, they only gave us room for that right here, but look at this graph. Aren't there two other points where y has a coordinate of 3? This point and this point. So let's write both of these as ordered pairs in function notation. So I'm going to say f of, and that looks like a negative 3 equals 3. And f of, what's the one we haven't done yet? Is it the one way over here? F of 9 also has an output of 3. And there you go. There are 3 points on that graph where y equals 3. And we've written all 3 of those in function notation. Now, when is this graph positive? On what interval? Well, it's positive most of the time beginning right here. All right. And then all the way to the endpoint 10 over here. But at this x value, the graph is not positive, it is 0. So I'm going to put an open dot on my left endpoint. And this is a graph of the interval where this graph is positive. So that's a half open interval. So we're going to have a parenthesis on the left and a bracket on the right. Parenthesis for the open dot, bracket for the closed dot. And what is this x value right there? And I think earlier, didn't we call that negative 6.1? So let's be consistent. And then what's the x value on this endpoint on the right? That's a 10. So this graph is positive on the open interval from negative 6.1 to 10, where x cannot equal negative 6.1, parenthesis, but can equal 10, bracket. When's it negative? Okay, it's the other part of this graph right here, this branch down here in quadrant 3. Okay, and I projected that part of the graph onto the x-axis. So there we go. There's a graph of the interval, but let's do this in interval notation. And this is another half open interval with a bracket on the left and a parenthesis on the right. And what's this x-coordinate there? Negative 8. And what's the x-coordinate at the open dot? I think we call that negative 6.1. So the graph is negative on the half open interval from negative 8 to negative 6.1, where x cannot equal that negative 6.1. Now, for what values of x is f of x greater than 3? Well, let's go ahead and graph the line y equals 3 up here on our coordinate plane. There it is right here. And now I see 2 intervals where the graph is above that line y equals 3. So we projected this first interval, but I have to be above, so I need open dots on both of those. And then over here again too, let's see. I'm going to do the interval notation for this first. And that looks like approximately from x equals negative 3 all the way to x equals positive 3. But that's the open interval. So x cannot equal negative 3 or positive 3, just everything in between. And then again, over here, all right, we're above. And again, I need an open dot on the left, closed dot on the right. So here's the graph. Let's write this in interval notation. Another half open interval with a parenthesis on the left and a bracket on the right. And what's the x value there? Is that a 9? And the x value at that endpoint would be a 10. So the half open interval from 9 to 10 where x cannot equal 9. All right, there's number 3. Boy, this is just putting everything together for you guys. All right, now look at this. The graph is a scatter plot. That means we're talking about a discrete function, if it is a function. Okay, so my first thought is, does this scatter plot pass the vertical line test? Well, wherever I draw a vertical line, it could only cross that graph at one point. So yes, it is a function. Now the domain. Now, the domain and range, we have done everything in interval notation so far today, but that's because our functions have been continuous, solid lines. All right? This function is discrete because this is just a scatter plot. It's just those points, nothing in between those points. So domain and range is actually easier for a discrete function because for the domain, all we're going to do is list the x coordinates of every point on this graph. All right, and we use set notation to do that. That's the birdie brackets. All right, so the x coordinate of this first point, it's almost 1, but not quite. But if you said 1 there, you know, we're approximating. I don't know, I'd call that like, I don't know, a 0.9 or something. Let's see, what did I do there? 1/2? Oh, I didn't look at that carefully, you guys. Look at the scale down here on the x-axis. All right, that's 1/2, 1, 1 and 1/2, 2. So this is scaled by 1/2. All right, so I approximated that with a 1/2. It's actually not quite to 1/2, but we'll call that close enough for our approximation. And then what's the x-coordinate of this point? It's a 1. What's the x-coordinate of this point? It's a 2. What's the x-coordinate of this point? It looks like approximately 3. That's a little off. And what's the x-coordinate of this point? Approximately 4. So again, the domain, all I did was approximate the x-coordinates of every point on the scatter plot. And the range, I'm going to do the same thing, but now I'm going to approximate the y-coordinates of each point. And your order really doesn't matter here, so I'm just going to work left to right. And I'm going to say a 3, and then a 2, and then a 1, and then a 1/2. And what would this then be? About 1/4? There you go, domain and range. In set notation, because this is discrete. That scatter plot is the graph of a discrete function. Now the extrema. Well, again, real easy here because I just look at the coordinates of the highest point and the lowest point. So the coordinates of the highest point, well, again, we call that x value 1/2, and the y value there is 3. So that's my maximum value as an ordered pair, and my minimum would be that point right there. So as an ordered pair, it looks like the x is 4, and what did we call that y? 1/4. There you go. Your max as an ordered pair and your min as an ordered pair. Now, increasing or decreasing. Well, look at your scatter plot. These points are decreasing within its entire domain. So I'm just going to rewrite the domain here. Well, that's decreasing. So the increasing, it's never increasing. So that's the empty set. It's decreasing within its entire domain, so I'm just going to rewrite the domain. The set 1/2, 1, 2, 3, and 4. 1/2, 1, 2, 3, and 4. Now the intercepts. Well, this graph never touches the x-axis, so there's no x-intercept, and it never touches the y-axis, so there is no y-intercept. There are no intercepts. Once again, the empty set. Now, function notation, f of 2 equals what y value? So I find x equals 2, and then what's the y value of that point? That's a 1. And now they say f of what x value is 1. All right, well, so when y equals 1, what's this x? It's a 2. Oh, did I not do that first one? So f of 2 equals 1, and f of what x value is 1? Well, that would have to be a 2. It's the same point right there. All right, know your function notation, you guys. Now, when is this graph positive? Well, again, all of these points are positive. They're above the x-axis. So it is positive within its entire domain. So once again, we're just going to rewrite this domain up here. The set 1/2, 1, 2, 3, and 4. The set 1/2, 1, 2, 3, and 4. When is it negative? None of these points are below the x-axis, so it is never negative, so that would be the empty set. And then for what values of x is f of x greater than 1? All right, so I need the points on this scatter plot where the y-coordinate is greater than 1. So there's my line y equals 1 right there, so it's only going to be these 2 points. So I need the x-coordinates of this point, and we called this one approximately 1/2, and this one is 1. And there we go. So that's number 4. Another great problem, and our first discrete function today. Number 5. Oh, no. Now that's what I call a scatter plot. And notice something here. Could I draw a vertical line anywhere that touches more than one point? Oh, look at over here. That vertical line, so at x equals -9, we have two outputs, 2 and 4. So there's an input that has more than one output, so this is not a function. It's just a grand scatter plot right there. That's a lot of points. And so f is not a function. Why? Because there's an input with more than one output. Every input does not have one and only one output. All right? Or does not pass the vertical line test. Okay, number 6. This is a continuous function, and it looks to me like it does pass a vertical line test. No matter where I put that vertical line, it's only going to cross that graph at one point, so we're going to say it is a function. And the domain would be, now I don't think I'm going to keep projecting because that's a lot of work, but I hope you can see this. All right, that's a x equals -2 on the left. And over here on the right, that's an x equals almost 1, 2, 3, 4. All right, so I'm going to do solid dot, so bracket, bracket. Okay, bracket, bracket. And then what was the x coordinate of this point? Well, that looks like a -2. And what's the x coordinate over here on the right? 1, 2, 3. I don't know, that's about, we have to approximate this. What do you think? I don't know, about 3.6, 3.7. Oh, look what I did. 3.6 repeating. That's 3.66666 on forever right there. And again, that's just my approximation. If you had called that 3.6, 3.7, 3.75, great. You might have even approximated that as the 4. And I would give it to you when you have to approximate. And also notice bracket, bracket, because the endpoints are part of the domain. Solid dots. Now the range. Now we do the same thing with our lowest y all the way to our highest y. And again, solid dot, so we're going to have brackets again. And what's the minimum y value here? -1, 2, 3, 4, 5, 6. That's a -7, isn't it? And what's the highest y value? That looks like we go all the way up to y equals 10 up top. So both the domain and the range are closed interval. The domain is the interval from -2 to 3.6 repeating, and the range is the interval -7 to 10. Okay, closed intervals. And remember, domain, that's all your x values on the graph. The range would be all your y values. Now the extrema. Well, we have a lowest point, that's a min, and a highest point, that's a max. So let's just write those as ordered pairs. All right, and the min, well, what's the x coordinate there? -2, 2, and what's that y value right there? Let's see, 1, 2, 3, 4, 5, -7. Sorry, I had to count them again, I forgot. All right, and now what are the coordinates of this point right here, that max as an ordered pair? Well, we call that x value right there. Didn't we call that 3.6 repeating? And what's the y coordinate right there? 10. Okay, there you have it. Now, increasing. Well, this graph is increasing within its entire domain. So all we have to do is rewrite the domain, the closed interval from -2 to 3.6 repeating. -2 to 3.6 repeating. And it is never decreasing, so that would be decreasing in the empty set. There you go. I love the empty set. And the intercepts. Okay, well, I see an x-intercept and a y-intercept. So let's write those as ordered pairs. And notice how I already know at the y-intercept x is 0. And when x is 0, it looks like y is -1. And at the x-intercept, y is 0. So that right there, and you know, we have to approximate that. I don't know, 1/2, 1/3. Let's see what I did. 1/3. Okay, there's my x and y intercept as ordered pairs. Now function notation again. Notice how we keep stressing the function notation. F of x equals 2 is what y value? So when x equals 2, what's the y coordinate of that point right there? 1, 2, 3, 4. That'd be a 5. And when y is -7, f of what x value is -7. So -7, that's that minimum right there, isn't it? So when y is -7, what is that x coordinate right there? Is that a -2? There you go. Now, when is this graph positive and when is it negative? And it has an interval where it is positive, and that's going to be everything above this point right here. Can you see my arrow? So that's going to be a half open interval. Note the parenthesis on the left. And we said that that x value right there was 1/3 all the way up to the x value of that point right there, which again, and we approximated that one earlier. What did we call that one? 1, 2, 3. I think we called that 3.6 repeating. There it is, 3.6 repeating. Now, when is it negative? Well, that's when everything's below this x-axis. So we're going to do a half open interval again, but this time we're closed on the left. So I'm going to go bracket and parenthesis, and the x coordinate of that point was a -2. And we called the x coordinate of this point where we're open as that 1/3. There you go. So this graph is negative in the half open interval from -2 to 1/3, where x cannot equal 1/3. And then finally, for what values of x is f of x greater than 2? Well, let's go ahead and graph y equals 2. There it is. When are we above that horizontal line? And that would be from x equals 1 to x equals at 3.6, but we have to be open on the left. So I'm going to go parenthesis 1 to 3.6 repeating, closed. And there you have it. I hope you're starting to get a feel for this. And I know it's seeming tedious, and I'm sure this is a lesson that is more than one day. All right, but I'm going to put this whole video together for you in one shot. I hope you're enjoying the show. All right, number 7. Wow, that's a cool graph. Now my question is it the graph of a function? Now a lot of people would say this does not pass the vertical line test, but look at how we have a solid dot here and open there. That means if I draw this vertical line, this point does not exist on the graph of the function, but this one does. So it passes the vertical line test. Now, if that had been a solid dot there too, then I'd say, no, it's not a function, and we'd be done. That would make this problem a lot easier, but that is the graph of a function. Now the domain, the x values. Well, what are the x values when I go from here and then I make a jump up and I go from here? That's one complete interval. So I'm going to go a closed interval here. So bracket, bracket. And what's the x coordinate of this point on the left? That's a 0. And what's the x coordinate of this point all the way to the right? That looks like what, a 21? And there you go. The domain is the closed interval from x equals 0 to 21. Okay. Now the range, all the y values. Well, I need my lowest y value and my highest y value. So that's my lowest y value right there. All right. And my highest y value looks like this 10 all the way up here. So that's going to be a closed interval. And what is this y value? Well, we have to approximate again. I don't know, maybe -2.75? Yeah, all the way up to, and this y value all the way up there is a 10. So the range is y in the closed interval from -2.75 to 10. Extrema, Well, I just need then the same thing I did the range. I now need to write the coordinates as ordered pairs of this point, which was, what did we do there? We're going to say, oh, it looks like I'm probably starting with the one on the left too, so let's do that. So what's the coordinates of this maximum value? Well, x is 0 and the y is 10. And this minimum value, the x is a little bit more than 18. I don't know, what? Could I call that like 18.2 maybe? I did 18.5. Well, I think that's a little off, but again, it's an approximation. So 18.5. And the y coordinate, we called that something earlier. What was that? A negative 2.75? There we go. Now, and again, I think I'm a little sloppy on that 18.5, but you know, I'd have to give it to you if that's what you said. I think it's a little closer to negative 18 than that. Anyway, let's move on. So, I need the increasing and decreasing intervals. Wow. All right. Well, we're going to increase here and here. All right, so we are increasing from that open dot on the left to the closed dot on the right. So what's the x-coordinate of that open dot right there? That is, looks like a 6. All the way to, what's the x-coordinate right there? 8. So we're increasing when x is in the half open interval from 6 to 8, where x cannot equal 6. And then we're increasing again over here. So this is going to be, that's closed dot, so bracket, bracket. And we're going from, what, 15, 16, 17, 18. And that's the one we called 18.5 earlier. And I'm going to do that again just to be consistent, all the way to 21. Okay? Now, there are two intervals then where we are decreasing. And that would be from this x value to that x value, solid dots. So that's an x equals 0 to x equals 6. And then from here to here, also solid dots. So let's go bracket, bracket. And that is an x equals 8 to, and then there's my 18.5 approximately again. Okay. So those are both closed intervals. Intercepts. Well, I see both. I see one y-intercept and I see two x-intercepts. Hope I counted for them all. Let's see. So the y-intercept when x equals 0 is a 10. And the x-intercept is, well, there's one right here. And that's going to be, what, 10, 11, 12, 13, 14, almost 15. What did I call that? 14.75. Pretty good approximation, 0. And you know what? It looks like one more than I didn't notice. So you guys make sure in your notes, what's the coordinates of this x-intercept? Wouldn't that be 21, 0? And it seems I forgot about that. Okay, so make sure you write the point in 21, 0 as an intercept. We have two x-intercepts on this graph. All right. Now, f of 6 equals, so I go to x equals 6. And what are the coordinates at this point right there? The y-coordinate is 4. So f of 6 equals 4. And when do we have an output of 7? Well, it looks like we have a couple points with outputs of 7. There's one right there. So f of, and that's approximately 1, a little bit less than 1. So I did 0.8. F of 0.8 is 7. But now, let's not forget about this point over here too. Not the open dot, but at this point here, we also equal 7. And it looks like I neglected to put that in, so you guys need to add this. Okay. F of, where's the 7 at? Right here. And it looks to me like f of 11 also equals 7. So next to your f of 0.8 equals 7, I'd put f of 11 also equals 7. Now, when is this graph positive? Well, it is positive from x equals 0 all the way to this x value right there. So 0, and what did we approximate this as right here? Did we say 14.75? Yes, we did. And again, notice we are closed on the left because this point is above the x-axis, but we're open here because we are equal to 0 right there. We are not positive, so we have to have a parenthesis on that end. And now when are we negative? In this interval right here. And we would have to be open dots on both sides. So that's parenthesis, parenthesis, and that's from 14.75 all the way to 21. But again, we're equal to 0 at those two endpoints, and that's why we had to go open, parenthesis, parenthesis. And then finally, for what values of x is f of x greater than 7? So notice how I graph y equals 7, and I'd be talking about this half open interval and this open interval right there. So I need a half open interval. All right, and that's from what? 0 to 1. And oh, I called that earlier not quite 1, so 0.8. And then we have an open interval here, and that is from x equals 6 to 11. And I said 10.9 right there. I approximated it. If you called that 11, I'd call that good. Wow, a lot going on here, and I'm starting to get real tired, but we're going to finish this out. I'm going to keep this video rolling. All right, so now number 8. The table on the right represents a continuous function defined on the interval from 0 to 6, the closed interval from 0 to 6. And that's why we see x is from 0 to 6. Now, I really do not like to model a continuous function with a table. I'd much rather have a graph, all right? And I could plot those points and then do a smooth curve going through all those points, all right? But they're doing this with just a table to make a little point. So we're going to have to do a little processing about our answers here. Now, our first thought is this a function? Now, based upon what they gave me on the table, it looks like every input has one and only one output. So I would call that a function. Okay? Now it is continuous, so there's no guarantee there because I can't see everything on this table, but I'm betting that this table does represent a function because it looks like every input has one and only one output. Now, what's the domain? Well, they already gave me the domain right here. It's the closed interval from 0 to 6. My minimum x value is 0. And my maximum x value is 6. So that's the closed interval from 0 to 6. That's 0 to 6 and everything in between. Now what's the range? Well, we're going to go from our minimum y value to our maximum y value. So it looks like the minimum y value here is a -3. Yep. And what's the maximum y value? To 20. So the range is y in the closed interval from -3 to 20. Now, extrema, if they exist as ordered pairs. So here's the y coordinates of my extrema in the range right here. All right, so I'm going to have the point 1, -3, and my max where y was 20, that's this point down here, and that's the point 6, 20 as an ordered pair. So here's my min as an ordered pair. There's my max as an ordered pair. Now, when are we increasing? Now, you see how we're decreasing and then it looks like we're increasing the rest of the way? So, you know, we don't see the entire function in this table, but it appears, and I'm going to say appears to be because I am not 100% sure, but it looks like this graph is increasing, or let's say we're increasing, let's start with that, from 1 to 6. So I'm going to go to the closed interval from 1 to 6. But I'm not 100% sure because I can't see everything. Was it decreasing? Well, it appears to be decreasing. See how I go from 2 to negative 3? From x equals 0 to 1. The closed interval from 0 to 1. Now again, and that I can only say that it appears because they gave me a table to model a continuous function. So I can't see everything with this table. Now the intercepts. Well, I'm looking for x equals 0 or y equals 0. There's an x equals 0 right there. So the y-intercept is the ordered pair 0, 2. Remember, at the y-intercept, x equals 0. Now, does y ever equal 0? Oh, yeah, right there. So the x-intercept will be the ordered pair 2, 0. There you go. Now, f of 4 equals, well, that's easy on a table. F of 4 equals 6. And f of what x value is 12. That's also easy on the table. When y equals 12, x is 5. So f of 5 equals 12. Now, when is this positive? Now, again, I can't see everything. So honestly, we don't have enough information because I don't know what's happening between 0 and 1 and 1 and 2. All right, all I see are these points. So I really don't have enough information to tell you where this graph of a continuous function would be positive or negative. Now, for what values of x is f of x greater than 0? And again, I can approximate this or make a conjecture. It appears to be, when are we greater than 0? Well, we went from 2 down to negative 3, and then, 2 and beyond. That's the part I'd focus on right here. So I'm going to go from x equals 2 all the way to x equals 6. I'm open at the 2 because that is 0. I'm closed at the 6 with the 20. But again, there's also a little interval right here from 0 to somewhere between 0 and 1. I went from positive to negative. And I just don't have enough information to even talk about that. Okay, number 8. Oh, now they do the same thing, except they're giving us a table to represent a discrete function on the interval from 1 to 5. Now, a table to represent a discrete function, that is very appropriate. All right? So, is it a function? I just look at the table. Does every input have one and only one output? Well, when x equals 1, I'm at 4, 2, 10, 3, 5, and so on. Yeah, this is a function. Okay, the domain. Now, I love this because this is discrete. So the domain is just my set of x values. Note the birdie brackets for set notation. 1, 2, 3, 4, and 5. And the range would be my corresponding y values. All right, and you don't have to put these in order. I'm going to put them in the order I see them. 4, 10, 5, 8, and 3. If you wanted to put those in order, you could. But I think it says a lot more when I put them in the order that I see them in the table. Now, extrema. So I'm looking for my minimum y or f of x value and my maximum. All right, my maximum y value is a 10, so as an ordered pair, that would be the point 2, 10. And what's my minimum y value? The 3. So that's the ordered pair, 5, 3. Now, increasing. Well, this is discrete, so I can talk about the interval where we're increasing. And since this is discrete, I'm going to use set notation. All right, so when x equals 1 and x equals 2, I go from 4 to 10. All right, so I'm going to go when x equals 1 and 2, this function is increasing. And then does it increase again? Well, oh yeah, when x equals 3 and 4, I go from 5 to 8. So from 3 to 4. All right, now where's it decreasing? Well, I'm increasing from 2, or decreasing from 2 to 3. Set notation, 2 to 3. And am I ever decreasing again? Yeah, from 4 to 5. There you go. Now, intercepts, if they exist as ordered pairs. So, do I have a y-intercept? Does x ever equal 0? No. Do I have an x-intercept? Does f of x or y ever equal 0? No. There are no intercepts. Function notation, f of x equals 3 is what y value? Well, when x equals 3, f of 3 is 5. And when I have a y value of 8, what x value gives me that 8? So f of what x is 8? So I find the y equals 8, and see that x right there, 4, f of 4 is 8. Now, when is it positive? Well, look at those y values. They're all positive. So that's within its entire domain. So I'm going to rewrite the domain. And that is that 1, 2, 3, 4, and 5. When is it negative? Well, y is never negative, so that would be the empty set. And then for what values of x is f of x greater than 4? All right, so not at 1, at 2, at 3, and at 4. And those are the x values where f of x is greater than 4. And that is number 9. That's a pretty cool problem right there. Now, number 10. The amount of daylight in hours dependent on the month of the year. Now, you guys, I actually went on the internet and I looked at the amount of daylight in Seattle, Washington, and they gave me like daily values and I had to convert that to monthly to make this make sense. So I created this table for you guys right here. All right. So the amount of daylight in hours dependent on the month of the year. So X is my month. That's like January, February, March, April, May, June, July, and so on. And then I researched, and guess what? The amount of daylight in total hours in January, where X is the month and f of x is the total daylight in hours. And this is in Seattle, Washington, by the way. So in January, we have 275 hours of daylight. In February, 284 hours of daylight. March, 366 hours of daylight. April, 408 hours of daylight. May, 468 hours of daylight. June, 477 hours of daylight. July, I think we're still increasing. Yes, 482 hours of daylight. Then I think we get to August, and I think it's in August where the days actually start getting shorter. Let's see. Yeah, 441 hours of daylight. September, 375 hours. October, 333 hours of daylight. November, 277 hours of daylight. And December, I believe that's the month where we have the least amount of daylight in Seattle, Washington, and that is 263 hours. Now, it took me a little time to come up with this, all right? But you guys are worth it. So there's a table representing the total number of hours of daylight based on any month. Okay, so is this a function? Well, every input x has one and only one output y, so yeah, it's a function. And what's the domain? Well, the domain, and this is discrete right here, the way this has been set up. So I'm going to use set notation, and I'm just going to list all my months. January, February, March, and I got lazy here, so I went ... and then I'm going to end with, and I like to work backwards here, watch. Oh, I didn't do it here. Usually I would do that, but now I'll go 10, 11, 12. And I'm just listing enough so you see the pattern. 1, 2, 3, and so on until we get to 10, 11, and 12. Now the range, I'm going to do the same thing. So, but here I have to list them all because there really isn't a pattern there now, is there? So we go 275, 284, 366, 408, 468, 477, 482, and then the days start to get, the light becomes less and less every month. So where was that? 441, 375, 333, 277, and then 263. Whew. Extrema, if they exist as ordered pairs. So when do I have, what month has the least amount of daylight and what month has the greatest amount? Well, looks like, what is that, 7? Is that July? We have 482 hours of daylight. So I'm going to write that as an ordered pair. And then December, we have 263 hours of total daylight. So there's 12,263 and 7,482. Increasing. Well, we're increasing from January, February, March, April, May, June, July. So let's write those in set notation. Month 1, 2, 3, 4, 5, 6, and 7. And then daylight starts to decrease. And that would be from 7 to 12. Okay, and I jump to the 8. Okay, 9, 10, 11, and 12. There you go. If you would have put 7 right there, because again at 7 we begin to decrease there, so I would have taken that either way. And the intercepts. Does x ever equal 0? We don't have a month 0. There's no y-intercept. And do we ever have 0 hours of daylight in any month anywhere? No, we don't. Guess what? There are no intercepts. Okay, number 11. Okay, wow. This is a context problem. Well, it's not even that really. They just have verbally described discrete functions. So the first term in a sequence is 36. Each consecutive term is exactly 1/2 of the previous term. So you know what? I thought at first maybe I should model this with a recursive formula, but I think it's going to be easier to talk about the features of this function if I do it as a table. So I'm going to do a table. All right. The first term in a sequence is 36. So x is my term number, and that term is 36. Okay. And then each consecutive term is exactly 1/2 of the previous term. So what is 1/2 of 36? 18. What is 1/2 of 18? 9. What is 1/2 of 9? 4.5. What is 1/2 of 4.5? 2.25. What is 1/2 of 2.25? That would be 1.125. And what is 1/2 of 1.125? That's like a 0.56. You know what? I don't want to make a mistake, so I'm going to do this on my calculator. Okay, if I can get my calculator set up here. So I'm going to go 1.125 divided by 2. And I'm getting 0.5625. There you go. So, and notice too, for my x's, because this is a sequence, all right, so we're going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. We just keep going and going and going. And my y's 36, 18, 9, 4.5, 2.25, and we just keep going and going and going forever and ever and ever. So first, is this a function? Well, does every input have one and only one output? Yes. The domain. Well, that would just be my x values because a sequence is discrete. So my inputs would be my term numbers. And that's going to be first term, second term, third term, fourth term, and they go on forever. So I'm just going to say and so on right now where I can see the pattern. Now what's my range? Now I'm going to do the same thing here. Those are my outputs. My y values are my f of x values. 36, 18, 9, 4.5, and I'm just 1/2 of the previous term every time, so I'm just going to go and so on right there. Now, extrema. Well, I have a maximum y value of 36, so let's write that as an ordered pair. When x equals 1, y equals 36, or the first term of this sequence is 36. Now, because I'm going on forever and ever and ever, all right, I'm approaching 0, but I never get there. So there will be no minimum y value. Increasing. Well, look at those y's. We're never increasing. We are always decreasing. So increasing would be the empty set. Decreasing, I'm always decreasing. So I'm decreasing within my entire domain. So I'm just going to rewrite the domain. 1, 2, 3, 4, and so on. Now intercepts. Well, x never equals 0, so there's never a y-intercept. And my y's are going to get closer and closer to 0, but never get there, so there's never an x-intercept. That's the empty set. Well, that wasn't so bad, was it? Number 12. Oh, now our context problem. Marcus bought a $900 couch on a 6 months interest-free payment plan. He makes $50 payments to the loan each week. So let's put this in a table. Okay, so he bought the couch for $900. So when he bought it, week 0, he owes $900. And he is paying $50 back interest-free every month. So in 1 week, he will only owe $850. 2 weeks, $800, and this pattern just continues. $750, $700, $650, $600, $550, $500, $450, $400, $350, $300, $250, $200, $150, $100, $50, and then $0. So it's going to take him 18 weeks to pay off this loan. So is this a function? Well, every input has one and only one output. And by the way, this is a discrete function. So yes. Oh, look at this. Let's model this recursively, just for practice here, okay? So let's go my first ordered pair in function notation. F of 0 is 900. And then f of x equals my previous term. And what's my pattern of change? We're subtracting 50 every time. Okay, recursive formula now. And I could have started with this, with the story problem right here. All right, but I don't think I could see everything as clearly as I can with this great table right here. Because now look at my domain. Well, this loan will go from week 0 to week 18. So it's a function. And then, again, look at what I did again here. I'm going to start at week 0, week 1, week 2, week 3, and so on. And this is where I like to work backwards because I don't want to count. So I'm going to go, I ended 18, there's 17, there's 16. So there's my domain. 0, 1, 2, 3, and everything in between until I get to 16, 17, and 18. What's my range? Let's do the same thing with our f of x or y values. So I start at 900, and note, I don't have to go in order here. I'm just doing the way I see them. 850, 800, 750, and I think you see the pattern, so I'm going to go and so on until I end at the couch is paid off. 0, 50, 100. And there's my range right there. Now, extrema. Well, the maximum I owed on that couch was $900, and the minimum I owed on that couch was $0. So I have a max and a min. There's my 0, 900. And there's my 18, 0. Increasing. Well, we are hoping this is decreasing, so it's never increasing. And it's decreasing within its entire domain. So I'm just going to rewrite my domain. The set from 0 to 18. Okay, and this is discrete, and that's why we had to do all this set notation. The intercepts. Well, I see a y-intercept and an x-intercept. There they are right there. So I'm just going to write those as ordered pairs. 0, 900, and 18, 0. Okay, number 13. Same problem, except this time each consecutive term is 1/2 less than the previous term. All right. So This sequence was what? Okay, pattern of change, minus 50. All right, so if I did a sequence, that would have been arithmetic. I'm thinking of the problem before that, though. But anyway, this sequence right here, 1/2 less than, that would be arithmetic. All right, so let's do a little table again here. All right, the first term in a sequence is 36. So term number 1 is 36. Each consecutive term is 1/2 less than the previous term. So this would be term 2, 35.5, 35, 34.5, 34, 33.5, 33, and so on. Okay, is this a function? Well, every input has one and only one output. Yes, that is a function. And what is the domain? Now, this is a sequence. So my inputs are term numbers, and that implies discrete. So I just need to list these x values in set notation. And I'm going to go 1, 2, 3, 4, and so on, because it goes on forever. The range, those are my y values. And again, set notation, and I'll just do them in the order I see them. 36, 35.5, 35, 34.5, and so on. That pattern just continues forever and ever and ever. Extrema. Well, we do have a maximum output of 36, so let's write this point as an ordered pair. X equals 1, y equals 36. Okay, but because I'm getting lower and lower and lower, all right, I'm going to go to negative infinity. So there is no minimum, only that maximum value. Increasing. Well, my f of x's are never increasing. Empty set. Decreasing. It is decreasing within its entire domain. So just rewrite the entire domain. 1, 2, 3, 4, and so on. Now the intercepts. Well, x never equals 0, so there's never a y-intercept. Will f of x ever equal 0? Well, we don't see it in the table I've set up right here, but I'm going to take you to a pretty cool place, and this is where we're going algebraically. Intercepts, okay? Y will eventually equal 0, all right? So let's figure out when, okay? So you know that this is arithmetic, all right? So you know an explicit formula could be linear, all right, will be linear. And look, I did slope-intercept, but I don't have a y-intercept. So I'm going to do this. 7, 6, 5, 4, 3, 2, 1. Let's go 0. And if x equals 0, let's look at the pattern over here. 35, 35.5, 36, 36.5. There you go. So let's write our equation. So what's my slope? Well, my pattern of changes, we're subtracting 1/2, all right? So that's my common difference. So I have a slope of negative 1/2. And what's my y-intercept? 36.5. There you have it. You could write that as a fraction if you wanted to, all right? But now I want to know, when is this y going to be 0? So let's solve this equation. Okay, so we're going to get rid of that negative 1/2 x by adding 1/2 x to both sides. Now bring down your equals. And we have on the left 1/2 x, and on the right the negative 1/2 x and the 1/2 x cancel, leaves us 36.5. And now we have to undo multiplying x by 1/2, so let's just multiply both sides by 2. And now let's rewrite again. So 2 times 1/2 is 1. 1x equals 2 times 36.5. Well, that'd be what? Man, I'm getting tired. It's tough to think right now. Is that 73? Yeah, x equals 73. So it's going to take to the 73rd term before my f of x gets to 0 right here. So my x-intercept is 73, 0. And there's a little algebra there for you too. Okay, number 14. An empty 15-gallon tank is being filled with gasoline at a rate of 2 gallons per minute. So is that a function? Well, yeah, because time's going to be my number of minutes, and we're just at the gas pump pumping gas in. So every minute there's going to be a different amount of fuel in my gas tank. So I'm going to say yes, that is a function. And the domain is going to be, so I'm just going right from this, aren't I? Well, when I start filling my gas tank, time is 0. And how long is it going to take for me to fill my 15-gallon gas tank if it was empty at 2 gallons per minute? Won't that take me? Wow, that's going to take a long time. All right, that's going to take 7.5 minutes, isn't it? Whoa, man, we got to get a quicker gas pump than that. All right, but I didn't write the problem. All right, so my domain is the closed interval from 0 to 7.5. Okay, what's my range? Well, my gas tank was empty, 0, and it fills at 15 gallons. So the closed interval from 0 to 15. And the extrema, well, 0, 0. When I started filling my gas tank, it was empty. We pushed it to that gas pump. And when it was full, it took 7.5 minutes to fill 15 gallons. 7.5, 15. Increasing. Well, it's increasing throughout its entire domain, so the closed interval from 0 to 7.5. When is it decreasing? Never. The empty set. And the intercepts. Well, see that 0, 0? There we go. And let's see. Will y ever equal 0? No, that's it. That's both of them right there. So that is it. 14. Wow. 15. For each equation, sketch a graph and describe the key features of the graph. All right, so let's go ahead and put an x-axis and a y-axis on this grid. Okay, and let's practice graphing y equals negative 2x plus 4. Okay, sorry, my allergies are acting up a little bit. I've been talking too long on this video. So the y-intercept is 4. 1, 2, 3, 4. And the slope is negative 2, so let's drop 1, 2 and run 1 right there. And if they just give me this linear equation, that would imply that this would be a continuous function, so I'm just going to draw the line through those 2 points, but then they restricted the domain. X is greater than or equal to 0. So I'm going to start at my y-intercept and work a ray through those 2 points. Just like that. Now, is that a function? Well, it looks to me like that graph passes the vertical line test. Yeah, it's a function. And what's the domain? Okay, well, closed on the left and open on the right, bracket parenthesis, and my left endpoint would be x equals 0. And my right endpoint, well, I'm going forever and ever to the right, so that's infinity. The range, okay, well, my y values. All right, well, negative infinity up to this y value up there. So I'm going to go open on the left because I can't reach negative infinity. But how high do I go again? 1, 2, 3, 4. Half open interval from negative infinity to 4. Extrema. Well, we have that one maximum value as an ordered pair. 0, 4. Increasing. Well, this is never increasing. It is always decreasing, so let's just rewrite the domain, the half open interval from 0 to infinity. And the intercepts. I see a y-intercept and an x-intercept. So the y-intercept would be x equals 0, y equals 4. And the x-intercept would be this point right here. And that's x equals 2, y equals 0. Oh, how cool. All right. Number 16. Oh, look at this, an exponential function, right on. Well, let's practice graphing exponential functions. You guys know that g of x equals 1 times 3 to the x power. The y-intercept is 1. All right, and then we're taking these outputs and multiplying by 3 every time because that's a base 3. So when x equals 1, I'm going to go up 1, 2, 3. When x equals 2, I multiply 3 by 3 to get a 9. And I'd run out of room, so I'll quit going this way. Let's go the other way. How about 1/3 of 1? How about 1/3 of 1/3? 1/9. And you know what? We're going to keep going and going and going and get closer and closer to the x-axis, but never quite get there. So there's my exponential growth curve right there. And is that a function? Why, yes, it passes the vertical line test. Domain, arrow to the left, arrow slowly to the right. That would be all real numbers. So negative infinity to infinity. Note the parentheses because we can never reach negative infinity or infinity. And the range, well, we're getting closer and closer to 0, but we never get there. So open, and I'm getting closer to 0. And to the right, I'm going up to infinity. So there we go, the open interval from 0 to infinity. Extrema. Well, I never reach 0, and I can never reach infinity, so there is no extrema. Increasing. Well, this graph is increasing throughout its entire domain. Negative infinity to infinity. Decreasing, never, the empty set. And intercepts, well, I don't have an x-intercept because I get closer and closer but never get there. But I do have a y-intercept at x equals 0, y equals 1. That's it. Oh man, that's it. Now, that was quite the activity right there. And I know in class we did not have time to cover all of it, but I thought I would give you guys a video. And I'm sorry I started to lose my voice at the end because I don't know, this video is the longest video I think I've ever done. All right. But I hope you enjoyed it. And this is more about you being able to go back and take a look at certain situations rather than sitting through and watching through the entire thing. All right. And I hope you guys are starting to feel comfortable with all these concepts on the features of functions right here. And most important, the notation to communicate your understanding of the features of functions. You guys have a great day.